For this lab, we were to observe the motion of an object that is dropped from rest and falls straight down. I recorded myself dropping a tennis ball and analyzed the motion of the ball dropped from rest using a video analysis software tracker. I then applied a fundamental principle, Newton's second law, to model the predictive motion of the object using VPython. I made two computational models, the first one considering only the weight force and the second one considering both the weight and drag force. I compared the observed position versus time data from tracker to the predicted position versus time data from the two models. My results were that the computational model that includes both the effect of gravity and drag predicted the motion of the tennis ball more accurately. However, the effect of drag did not have as much influence on the motion of the ball as expected. Newton's second law is a fundamental principle in physics. It states that the final velocity of an object is equal to the initial velocity plus the net force acting on the object divided by the mass of the object times delta t, the change in time. In the case of the tennis ball that is dropped from rest, the initial velocity is 0, but its velocity does not remain constant as the ball falls down. Therefore, the change in velocity does not equal to 0. In order for that to happen, the net force acting on the object must not equal 0. We can assume that the effect of gravity and air resistance causes a non-zero net force. Here is the video of the tennis ball in tracker. The axis is oriented so that the ball starts at the origin and travels in the negative y direction. I marked the center of the ball after each frame to extract position versus time data. The graph of the position versus time data has a negative slope that is increasing, which means that the ball is speeding up. I will use these data points to compare with the data in my computational models later. First, I made a model in VPython based on Newton's second law, only considering the force of gravity or weight force. The mass of the ball is 0.057 kilograms, and both the initial position and initial velocity are 0. I picked delta t really small compared to the total time of the observation, which was 0.4 seconds. G is the gravitational constant used in the equation to determine the force of gravity. J hat is a unit vector that points in the positive y direction. B, the proportionality constant for drag force, is 0 in this model because we are only considering the effect of the weight force. Here is the while loop where we are considering t less than 0.4 seconds. The equation for the weight force is inserted here, and the net force is equal to the weight force since we are only considering the effect of gravity here. This is Newton's second law, where the final velocity is equal to the initial velocity plus the net force divided by mass times delta t. The final velocity here is used in the position update equation to predict the ball's new position. Here is a graph of the observed position of the ball and the predicted position of the ball with the force of gravity as the only force. As you can see, in the beginning, the observed and predicted positions match each other perfectly. This is because we use the initial conditions in the computer code. Since the model is over-predicting the position of the ball as t increases, we can infer that there is an additional force, air resistance, that is causing the ball to slow down. The second computational model takes both the gravitational force and the drag force into consideration. There were a couple of changes made to the code. The equation for the drag force, Fd, was added here. This makes the net force equal to W, the weight force, plus Fd, the drag force. The value of B was estimated and checked until the final output of the computer model matched the final observed position, which was negative 0.768. Here is a graph produced by this computer model. It looks similar to the previous two graphs, but let's compare them further. This is a graph of the observed position and the predicted positions, one considering weight force only and the other considering both weight and drag force. There is not much difference between the two predictions made by the two computational models. This could mean that air resistance did not significantly affect the motion of the ball in the time interval observed. The model considering drag force was closer in predicting the motion of the ball. However, there is still a disparity between the observed and predicted positions. This could be attributed to human error. Since the tennis ball becomes extremely blurred, it was difficult to pinpoint the position of the ball as t increased. Towards the middle, I underpredicted the position of the ball, when in reality, the ball traveled further than I observed. The terminal velocity of a falling object is the velocity when the magnitude of drag force equals the magnitude of weight force. Since these two are opposite in direction, the net force is zero and the velocity is constant. The model with drag predicts a terminal velocity. The pink graph, model with drag, approaches a zero slope as t increases, indicating a constant velocity. The blue graph has a constant non-zero slope, indicating a change in velocity. If the object were thrown instead of dropped, the terminal velocity would be the same in both cases. If an object is thrown, the initial velocity would not be zero. To test what would happen, I chose the initial velocity to be 0, -5, 0. As the graph shows, the object would reach the same terminal velocity. The graph of the velocity of an object dropped reaches a slope of 0 at -10 meters per second. At the same velocity, the graph of the velocity of an object thrown reaches a slope of 0 as well.